All right, when you introduce mercury atoms in here, it turns out that a sample of mercury has 7 different naturally occurring isotopes. You can see by these 7 different strikes here. This is what we call a mass spectrum. The mass spectrum, you see, some strikes here near 196. A mass spectrometer can weigh these atoms to a very high degree of precision. So, this is slightly less than 196, so it'd be 195 point something, 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 something. And so we get a very precise mass here. This one is around 198, just slightly less. And so again, we can get these masses to 6, 7, 8 sig figs. But not only do we get the weight of the atoms, individual atoms, but we also get 2 other bits of information. One, the number of naturally occurring isotopes, that is 7, and the percent natural abundances. And so looking at the strikes here, and you can see it here visually, for every 5 of these, we only get 1 of these. And so it looks like the isotope that has a mass close to 202, is the most abundant, the most strikes. The isotope that has a mass around 196 is least abundant. And so we can normalize this and then determine the percent natural abundances and the masses of each of those isotopes. So let's take a look at the numbers here. So that one that has a mass near 196 must have, because the mass of the atom is mostly protons and neutrons, so it's going to have a mass number close to 196. Its mass is not 196, but it's close to 196, right? And so mercury 196 has a 0.146% natural abundance, whereas mercury 202 should have much higher. This is mercury 202, this is 29.8, which is the highest out of all these. Now, if we were to introduce fluorine in the mass spectrometer, it would look quite a bit different. If we take a naturally occurring sample of fluorine and then just put a stream of atoms, ionize them, we only get 1 strike on here. And so there's only 1 peak in the mass spectrum. What does that tell us? If there's only 1 peak in the mass spectrum, it tells us that fluorine only has 1 naturally occurring isotope. And that isotope is fluorine-19. And so all atoms of fluorine weigh the same amount because they all have the same composition. And that amount is given on the periodic table, 18.998403. That's where I got the mass from. But many of those elements have multiple naturally occurring isotopes. So mercury, let's take a look at the mass of mercury off the periodic table. It's 200.59. 200.59. Do I see a peak here at 200.5 or 200.6? There's no peak there. And the reason there's no peak at 200.59 is because that mass on the periodic table is what? The average. It's not just the straight average, it's the weighted average of all these isotopes based on their fractional abundance here. And we wrote the equation up on the board, but you'd have more entries there rather than just 2. And so 100% of the fluorine atoms are fluorine-19, whereas mercury has a mix of 7. And so by looking at the periodic table, do you know how many isotopes? For example, if I asked you how many naturally occurring isotopes are there for nitrogen, can you tell me by looking at the periodic table? No. The only way you could do that is to run the nitrogen through a mass spectrometer and determine how many peaks. Well, somebody's already done that, and then they put it into something called the table of isotopes, where you can look it up. In the table of isotopes, you'll see all the naturally occurring isotopes of nitrogen, their percent natural abundance, and the mass of each isotope to many, many sig figs. But when we look at the average is around 14, so that kind of tells me that most likely the most abundant isotope of nitrogen will be nitrogen 14. Now, that's clearly the most abundant. Okay, there are, fluorine is an example of 1 naturally occurring isotope. There's another common element that also has 1 naturally occurring isotope, and that's phosphorus. Do you know what the isotope of phosphorus has 100% natural abundance? Look at the periodic table and tell me what isotope of phosphorus has 100% natural abundance. Not 30, 31. P31 is 100% natural abundance. P32 is a man-made radioactive isotope, and so that doesn't normally occur naturally, so that's not factored into the mass there. Fluorine does have some radioactive isotopes as well, but that's it for that. How do you make man-made isotopes? You know, naturally occurring isotopes, that's just what occurs in nature. Man-made isotopes are made by nuclear reactions. And let me see, I forgot to discuss one thing here. You know, here we have some radioactive material. The radioactive material has unstable nuclei, and as the nuclei decay or decompose, radiation is emitted. And we have different types of radiation. Alpha particles. Alpha particles are little chunks of nucleus that break off, 2 protons and 2 neutrons. Those are what Rutherford shot at them. Gamma rays, that's high energy light, gamma rays and X-rays. X-rays, they use, you know, Millikan used X-rays. He used X-rays to knock electrons off air molecules and had those electrons attached to oil droplets. And so gamma rays and X-rays, high energy light. Beta particles, have you ever heard of beta particles? Beta particles are electrons. They're just made up of electrons. And so why do they call it like cathode ray? Cathode ray is because those electrons originate at the cathode, right? Beta particles, why don't they just call them electrons? They don't call beta particles electrons because of where the electrons originate. Beta particles actually originate in the nucleus. And so how many electrons are found in the nucleus? None. There are no electrons in the nucleus. And so how can electrons emanate from the nucleus? Does somebody know? A nuclear decay process takes place. In the nuclear decay process, what happens is a neutron is converted into a proton. And so if a neutron gets converted into a proton, it spits out an electron. Maintain charge balance. Does that make sense? And so these electrons that get spit out of the nucleus are called beta particles. And that comes from radioactive nuclei. And so sometimes having too many neutrons is not good. You know, and that leads to radioactive properties. But we aren't interested in nuclear properties. We're interested in chemical properties. And so let's take a look at an example of chemical properties. If I were to feed hydrogen into the mass spectrometer, how many peaks would I get? I could get 2 or 3 peaks, depending on the sample of hydrogen. One peak will consist of this, where I have 1 proton and 1 electron. This is the hydrogen 1 isotope, H1. And then another peak, which is much smaller, is a little heavier. It's about twice as heavy, because it has a proton and a neutron in the nucleus. A proton and a neutron in the nucleus means, we call it H2, because now there's a proton plus a neutron, there's 1 plus 1 gives us 2. And so hydrogen 2 also has another name, it's called deuterium. Okay, now that it has a proton and a neutron, is hydrogen 2 a bigger atom, a smaller atom, or the same size atom? Hydrogen 2, what would you say, bigger atom, smaller atom, or the same size atom? I'm just rough. Smaller? Why would you say smaller? Because of the charge of the proton? Did the charge of the proton change here? The charge of the proton didn't change. The proton's still +1. And so, should it be bigger, smaller, or the same size? The same size. It's the same size, except it weighs more. So what's changed? If it's the same size and it weighs more, then its density should be bigger. For sure, it's going to be more dense, right? And so if you have a deuterium instead of a hydrogen, well, this one's going to weigh more. It's heavier. about the same size. There's going to be a little bit different gravitational, of course. But what about its chemical properties? Did you know if you drink a glass of water, you just drank some deuterium? Is it bad for you to drink deuterium? What's it going to do chemically? And so chemically, is hydrogen 1 and hydrogen 2 the same or different? Two choices. Same chemically or different chemically? Different? Why would they be different chemically? Well, what is the most important force in chemistry? Electrical. Does having a neutron there change its electrical properties? Are the electrical properties different here? Well, maybe because it is a little bit bigger, but other than that, are they all that different? No. Could you taste the difference between deuterium and hydrogen in your water? Did you taste the difference? Ah, got some deuterium in there. No, you can't taste, because chemically they're the same. You got a proton, you got a proton, you got an electron, you got an electron. That's the same thing, chemically, right? And then we have one where you don't want in your water. You don't want tritium or hydrogen 3 in your water. Why don't you want tritium or hydrogen 3 in your water? Well, tritium or hydrogen 3 has a proton and 2 neutrons in the nucleus, an electron. And so it's 3 times more, roughly, than hydrogen 1. And so this is going to be the heaviest or the densest of all the hydrogen atoms. It should be about the same size. And chemically, does it behave the same? Wait a minute. Wait, tritium. Have you heard of tritium? Tritium is radioactive. Tritium is radioactive. You don't want to be drinking this stuff, right? But radioactive, is that a chemical property or is that a nuclear property? It's a nuclear property, so chemists don't really care about that, except they stay away from this. Tritium, would it behave the same chemically as deuterium and hydrogen 1? Yes. So tritium undergoes the same chemical reactions and chemical processes as all those others. The only problem is its nucleus is unstable. Maybe this nucleus has too many neutrons, making it highly unstable and therefore radioactive. So tritium will probably want to undergo some sort of a reaction to make it more stable. All right, so if we feed a sample of hydrogen, we're going to get different strikes. And based on the average mass, which one's the most abundant? Take a look at the average mass and tell me, out of these 3 isotopes, which one are you going to see mostly? So if you drink a glass of water, you're drinking mostly hydrogen 1, because the average atomic mass is close to 1.0 U, which is close to the mass of the hydrogen atom. And so, that. All right, what was I going to do next? Oh, next, we're going to make this a little bit more complicated. I don't want to make it too complicated. Normally, you know, chemically, all these water molecules are the same, right? But they weigh different amounts because they have different isotopes. And so how many different water molecules did you consume in a gulp of water? How many different water molecules did you just consume in a gulp of water? And so rather than starting off with that, that's a typical question I give. I think I gave that question on the last exam 1 last year. I'll post my old exam from last year on so you can see. In fact, I did give that question last year. How many water molecules? Not only that, I made it a little bit harder. I asked how many water molecules and what percentages did you just consume? And so rather than doing that, because this is 3-atom molecule, let's do something easier. Let's do a 2-atom molecule. Okay. And so we're going to do a 2-atom molecule, and let me make sure I didn't forget anything. Let's just put up that. Number 80. So if you feed chlorine in a mass spectrometer, we're going to get 2 peaks. One peak corresponding to chlorine 35, one peak corresponding to chlorine 37. So there are only 2 naturally occurring isotopes of chlorine. One of the isotopes weighs 34.9689 U, so it's very close to 35, so this is going to be chlorine 35. It has a 75.77% natural abundance. The other peak is chlorine 37, which has a 36.96, or roughly 37 mass, 36.9658 U mass. And what's the average mass of the chlorine? And so if I have chlorine 35 and chlorine 37, what's the average of 35 and 37? 36. But you know, that's not a weighted average, that's a straight average. And so if you have 35 and 37, then a 50-50 mix will be 36, right? 50-50 mix. But we know what the average mass is because up on the periodic table we're given the average mass. What is the average mass? The average mass is 35.453. If the average is 35.5 roughly, that tells me it's mostly chlorine 37 or chlorine 35. It's mostly chlorine 35, and in fact it's a quarter of the way here. And so if this is 50% 35, this must be 25% 35 because it's farther away. This must be 75% 35. Do you see that? This is a linear relationship like we've seen before, and it makes sense. It should be a linear relationship, right? And in fact, it is. It's about 75% 35, like you'd expect. You know, when you look at the average. Okay, then we go to bromine. Bromine has 2 naturally occurring isotopes, bromine 79 and bromine 81. Look at the average. What's the average mass of bromine, roughly? And so one isotope is 79, the other is 81. What's the average on the periodic table? The average mass of a bromine is 79.9. 79.904, that's close to 80. And so the average mass of bromine is 80, which tells me it's about a 50-50 mix of the 2 isotopes, and in fact it is. Bromine 79 is 50.69%. Bromine 81 is 49.31%, so roughly 50-50. And we can just kind of visualize that based on this linear relationship. Okay, well, anyway, we get these numbers in the mass spectrometer. Remember, we can weigh these quite accurately and quite precisely. Quite accurately because we can calibrate with our carbon-12 calibration standard, and quite precisely because these are very sensitive instruments. And so we're looking at the molecule bromine chloride. Bromine chloride is a bromine bonded to a chlorine, called bromine chloride. Okay, the thing is, if I have a sample of bromine chloride, how many different bromine chlorides are there? Well, chemically, they're all the same, but they weigh different amounts. It's just like chemically, all these water molecules are the same, but some are heavier, some are lighter. And so how many different ones do we have? Well, we have 2 choices of bromine and 2 choices of chlorine. And this is like Legos or something like that. You put them together, and how many different combinations can you generate? And so if you have two choices of bromine and two choices of chlorine, how many different options are there? Seems like 4. But, you know, the easiest is just to draw them out. And so bromine can be 79 or 81. Let's start with 79. Chlorine can be 35 or 37. So let's start off with 35. And so this is 1. Okay, what's the next one? Bromine, we'll leave it at 79. But now we'll change chlorine to 37. This one weighs 2U more. It's a little bit heavier. You see that? And then the next one will be a bromine with an 81 and a chlorine with a 35. The next one will be bromine with an 81 and a chlorine with a 37. So that's 4. Can you think of others? Are there any other combinations here? No? Looks like 4. How about this? What if I do this? If I do chlorine 35, bromine 79. How about that? Is that different? Or is that redundant? Is double counting? Maybe. Let's just, or is it? Chlorine 35, bromine 81, should I count that or not? Now technically these aren't unique, right? These are duplicates of the previous one here. All right. So far we're going to get 4. And so is it possible to weigh individual molecules? Do you know how we can weigh molecules? Individual molecules? We can weigh them with a mass spectrometer. The only thing with molecules is you have to be careful. Let's look. You have to be careful with molecules, how you ionize them. You know, if your ionization source is too strong, it could break apart the molecule and fragment it. And so you do a gentle ionization of this, and then you can see. And so if we introduce a sample of bromine chloride into the mass spectrometer, how many peaks will we generate? 4. Now, which one's going to be the most abundant? The one that's going to be most abundant will be, you know, chlorine 35 is more abundant than 37. And so what's more abundant, 79 or 81? 79. So this will be the most abundant. And then we can go on from there. That's qualitative, right? The least abundant will be the ones with the least abundant isotopes. But we're going to do this quantitatively. We're going to figure out the percent natural abundances using dimensional analysis. And so using dimensional analysis, what is the percent natural abundance? And so here, let's start off with the first one, which we were thinking this is the most abundant anyway. A bromine 79 and a chlorine 35. Okay. Let's look at the natural abundances here. Bromine 79 is 50.69%. 50.69%. Chlorine 35 is 75.77%. If I multiply these together, what are my units? I don't know the equation for doing this. But we're going to figure out what the equation is by using dimensional analysis. And so the first thing I'm going to do is try to multiply these together. And so if I take 50.69% times 75.77%, what are my units here? Percent squared. Does percent squared make any sense at all? No. This is not the correct formula. So, you know, what do I need? I need the percent natural abundance. So what is the percent here? And so in the end, the dimension has to be in terms of percent. Only 1%. I mean, percent sign. And so how can I figure out what the formula is? I got to get rid of one of those percentages, right? And you know what the definition of percent is? What is the definition of a percent? Part per hundred. And so what if we do this? One easy way of getting rid of the percent sign is just divide by 100. And so if we got 50.69%, or in other words, a percent is 50.69 out of 100. And so 50.69 out of 100 atoms is bromine 79. We can't have 0.69, so another way of thinking about this is 5,069 bromine 79s for every 10,000 atoms. We just move the decimal place 2 over. That should do it. About 50.69 out of 100 are bromine 79, and out of that they're going to bond to chlorine 35, which is 75.77% of all chlorine atoms. And so we're going to, the percentage is, what percentage of the chlorine is the chlorine 35? Based on this is going to give us what, as far as a percentage goes? So can somebody calculate the percentage here?
38.4.
38.4. Give me more sig figs because we're allowed 4. I want to carry to 5.
078.
078. All right. Then let's go to the next molecule. The next molecule is this one, right? So let's try that. It's going to be bromine 79 with a chlorine 37. And so out of all the chlorine 35s, only 75.77 are going to be 35. The other are going to be 37. So bromine 79 with chlorine 37. And so bromine 79 is 50.69 out of 100 parts. And the chlorine 37 is 24.23%. And so what percentage of the chlorine 37s, which makes up 24.23% of all the molecules, is bromine 79? That's the way we read this. And what is it? 12.2821. I have more sig figs than I'm allowed. And then we go to bromine 81. Bromine 81 with chlorine 35. Bromine 81 was 49.21 out of 100 of those. And then the chlorine 35 was 75.77%. And that gives me 37.286%. And then finally, the last one is bromine 81 with chlorine 37. It's going to be 49.21 out of 100 parts will be of this percentage, 24.23%, which gives me 11.923. And then we double check this. We add up all the percentages and hope that it comes out to 100%. Does the sum of the percentages come out to 100%? Here's where round-off error might not make it come out to 100%, because if we round all these, it probably won't come out to 100%. What does it come out to? 99.9. That's 99.90%. We're off. Are we missing 0.1%, or is that due to round-off error? Are we missing 0.1% of the total, or is that due to round-off error? This is due to round-off error. If we carried all the digits all the way out, it should add up to 100%. So this is due to round-off error. Why did I end? Oh, I know why I ended early. Just to skip something. It's all right. Any questions about this? Water is quite a bit harder. Water is a step harder than this. When you do water, you could try this at home. When you do water, you'll see your percentages might not add up to 100%, and it's not because of round-off error. It's because you're missing something statistically. And so water is a bit more challenging. This is a lot easier. All right, any questions on this? We're going to continue with chapter 2 next time, but I'm not going to end early. We're going to have another pop quiz. I said we're going to have a pop quiz every week. We don't have an exam, so today is Thursday. It's the last day. It's the last chance to get a pop quiz. This pop quiz is going to be worth 5 points. And so this is not a practice. This is a real one. But the same rules apply. I want you to determine the percent methanol in a methanol-ethanol mixture. Given the density of the mixture is equal to 0.7900 grams per milliliter. Recall that the density of methanol was 0.7914 grams per milliliter, and the density of ethanol was 0.78. Was it 7984? Somebody remember the density of ethanol? Wrote it down. 7894, 7814, 7894. 7894 grams per milliliter. Thanks. All right, comment on the precision. Okay. All right, so the same rules apply. You could work with your neighbor or your friends. It's open book, open notes, open everything. Unlike exams are going to be all individual.